This is actually going to be an experimental talk. Unfortunately, that means we have to compare it with Mike Manfra's beautiful talk. The experiments are much more complicated, but I'm very excited that I think, so the very nuanced title is because I'm really excited, and I think we've actually finally shown that this is the truth, and I don't want to overstate it. I'll get to that in a minute. Like many of the other speakers, I was corrupted early in life by Tony Leggett. I fell in love with thinking about macroscopic quantum coherence, which is what we called qubits in those days, and have been fairly obsessed with these ideas ever since. I don't have good stories, but my wife is an artist, and she tells me that a picture is worth 1,000 words, and this doesn't seem to work. I think we have to click right here. Yeah, how do I do that? There. Yeah. Good. So this is a picture from ITP in Santa Barbara from a long time ago, in case you, it's still not working.
It just advanced.
Oh, it did. Yeah, here you can recognize some familiar figures, albeit in disguise. Okay, so now back to the talk. This work just appeared on the archive this week, and there's another paper, a negative result, which is a very important part of this story, that also appeared this week on the archive. I'm proud of this. I'm not a co-author on this paper, but I've been trying to convince the authors of this paper to post their negative result for a long time, and people just don't seem to like to post negative results. So we'll encounter that in a minute. Good. So let me, since not everybody here is a cuprate nerd, let me summarize where we are in our understanding of the cuprates. So the first thing is that we really now know more or less everything about the insulating parent state. It's a nearly classical Niel antiferromagnet. The low energy physics is entirely captured by spin wave theory. It's a beautiful theory, but it's understood. In large part due to both theoretical prompting by Tony Leggett and by various experimentalists and other theorists here, we really know that the superconducting state is D-wave. And while that's now sort of trivial, that's really a big deal also. The low energy physics of this phase is also completely understood. It's completely dominated by the nodal quasi-particles of BCS theory. The one thing that's a little bit exotic about the superconducting state is that the superfluid density is very low, so that phase fluctuations are an order 1 effect in the cuprates, and the consequences of that statement have not fully been understood yet. It's clear, however, that it has nothing to do with the system being close to a BCS to BEC crossover. And finally, there's an incredible complexity of other ordered phases that you just can't get rid of. They're there. At first, we sort of thought that maybe they were properties of one material or another, and we could find the right material to study that wouldn't have this complexity. But this complexity of many different or intertwined orders, in particular charge density wave and spin density wave or stripe orders, seem to be ubiquitous in the superconducting range of parameters. Here's a phase diagram that summarizes some of this. I'm not going to walk you through what all of these notations mean. You're just supposed to see that it's really complicated. But there is one other order that's part of this intertwined orders, maybe, that's been discussed for 1 or 2 decades. Eduardo and I have been obsessed with this for a long time. This is the role of pair density wave order in this. And so there are there are 3 positions. One is pair density waves don't exist. The second is that pair density waves exist, but maybe only in small corners of the phase diagram. And then there's the third and most spectacular proposal that the pair density wave is the mother of all orders, the source of the pseudo gap, and the essential thing to understand everything about the cuprates. Okay, let me define for you what a pair density wave is. So if I look at a superconducting order parameter, that's the expectation value of some electron pair creation operator. Here, big R is the center of mass position of this pair, and little r is the relative coordinate of the 2 electrons in the pair. Unconventional superconductivity, of which D wave is an example, is such that for any fixed position, the integral over the relative coordinate gives 0. This distinguishes unconventional from conventional superconductors. A pair density wave is that for any fixed relative coordinate, the integral over space of the center of mass coordinate of the pair expectation value is 0. Both of these any of these states are superconducting states in that they break the U1 symmetry of charge conservation. There's an analogy that I'm going to make several times here, which is the pair density wave state is to the uniform superconducting state as a spin density wave or antiferromagnetic state is to a ferromagnet. These both are magnetic. They both break time reversal symmetry, but they have very different properties because of their spatial structures. Okay. The sorts of pair density waves I'm going to have in mind is we're going to have the case where we have a pair field that has perhaps a uniform piece, which I'll call delta naught. It might have a D wave form factor. That's not going to be important in this discussion. And then there's going to be a modulated piece at some wave vector Q. These are 2 independent complex order parameters in this case. I'm also going to be talking about diffraction experiments. So the charge density is going to be an important player in the discussion. And the charge density is some uniform piece. Then if there's a charge density wave, that's described by a single complex order parameter and a wave vector K. But if we had these modulated superconducting orders, then we're going to also get induced density wave order from a gauge invariant combination. So this is delta star delta, this is gauge invariant, but it oscillates at period 2q. Or as a cross term between uniform and pair density wave order, we're going to get something that oscillates at 1q. In the problems that I'm going to be looking at, there is a commensurate lock-in between the putative pair density wave and the very clear charge density wave. And you can imagine that if you have this wanting to make charge density oscillations at 2q and some other physics making you want to have oscillations at k, if they're anywhere near each other, there are going to be terms in the Landau theory that lock them together and cause them to be mutually commensurate with each other. Okay, now the reason I'm not going to talk about theory is while there's a lot of theory, we've worked hard on this, there's a lot of things I'm proud of, but there really isn't a satisfactory theory that I can look you in the face and say, we really understand this, we know where it's going to occur and why. for uniform superconductivity, conventional superconductors, the BCS theory is really, very satisfactory. For unconventional superconductivity, at least we have a clear understanding of how it arises out of some sort of Kohn-Luttinger type mechanism. There's no similar understanding of even simple limits of models where we can generically say that there is a pair density wave ground state. We just sort of have to hope. But what I'm now going to try to describe to you is there's strong phenomenological evidence that a pair density wave exists in certain cuprates. And the punchline of my talk is going to be new data, the observation of the long-sought 1Q peak in a diffraction experiment. That's the paper I highlighted at the beginning. And this is different. Pair density wave was invented as an explanation for a bunch of dramatic experiments that I'm about to describe. But you're always a little suspicious of explanations. This was a prediction. And so I think that should be viewed in a different light. Okay, if you want to know about our attempts at a theory and some disagreements about perspective, here is a recent negotiated treaty that was published in annual reviews of condensed matter physics. So, yes. So that's what these two, so that's exactly what these two perspectives are. There is I'm going to be happy, okay. My punchline is it occurs in some very special corner of the cuprate phase diagram. It's strongly subdominant to uniform superconductivity, so it only occurs in places where you've done something really nasty to the uniform superconductivity. But the Patrick Lee, Seamus Davis, mother of all states, says it's exactly the opposite, that it's everywhere. And I'm going to present evidence against that as well. Okay, so here's the material that's going to be the star of this show. This is lanthanum barium copper oxide. Don't sneer at it. This is a very important material. It was the first discovered high temperature superconductor. So it has this very complicated phase diagram. It's got a weird low temperature tetragonal phase, which is something to do with tipping of oxygen octahedra, which makes it the most strongly charged and spin density wave ordered of the whole doped cuprates. It has this deep 1/8 anomaly, that is to say the superconducting TC has a deep minimum right at 1/8 doping. This is a somewhat special cuprate. And we're going to sit more or less right at 1/8, where all of this stripy business is strongest and uniform superconductivity is weakest. And what's seen by John Trinquata some time ago is really extraordinarily spectacular. So what's being shown here is, in blue, is the resistance in the C direction, perpendicular to the copper oxygen planes, as a function of temperature. In green, the resistivity in the plane, the AB resistivity. This has been rescaled by a factor of 10 to the third. The high temperature anisotropy in the resistivity is a factor of 1,000. But what you can see is that as the stripe order develops, the anisotropy increases, but then something very dramatic happens. The system roughly looks like it goes superconducting in 2 directions while remaining highly resistive in the third. These two curves are the magnetic susceptibilities measured with the magnetic field either perpendicular to the AB plane, to the copper oxygen plane, or parallel to the copper oxygen plane. The main thing I want you to focus on is that the Meissner effect, the full superconducting state, occurs at a much lower temperature, 4 Kelvin in this particular material. Okay, so that's very dramatic. Here's these same things on a logarithmic plot. You can see that the resistance doesn't really quite go to 0 here. It has some long tail. It's dropping by many orders of magnitude. So this is something that's almost superconducting, not quite. And the C-axis resistivity goes to 0 at some much lower temperature.
So it goes to 0 at 16 or 18 Kelvin.
Well, it goes below measurable at some point. You can fit this to a Kosterlitz-Thouless form if you want, and then you can extrapolate to where it goes to 0. You know, if you ask me, I don't think it goes to 0. Can't make a consistent theory if it goes to 0, but it at least gets very small. So it's, you know, more or less superconducting. Whoop. Come on. Yeah, there we go. These are complicated materials, and I've been worried about taking these experiments too seriously. You know, complicated materials can lie to you. But in the intervening years, more or less this same phenomenon has been observed in a large number of admittedly closely related materials, but really distinct materials, multiple distinct crystals of these materials, and in experiments carried out in different ways by multiple different groups. So I believe that this is really a fact. Now, why is that so surprising? Well, let me remind you that as we develop order in 2 dimensions, we expect systems to become more isotropic, not less isotropic. And so let's imagine that we have, say, some planar 2-dimensional XY ferromagnet. That's my model of a superconductor. And then we have some interplane coupling between the magnetization in plane J and J+1. And then what you would at first say is that as long as J perpendicular is small compared to the temperature, maybe I could ignore it. But that's not the case. You get block spins in each plane. As the correlations in plane develop, you should be thinking of locking a correlation area worth of spins in neighboring planes, and the interplane coupling becomes important when this quantity gets to be of the order of the temperature. So that means that J effective is large in proportion to the square. It's small in proportion to the ratio of these bare couplings, but it's large as the 2D correlation length gets large, so the system should become less and less anisotropic. Now, oh, come on. And, you know, you'll get, for instance, you'll never see 2D Kosterlitz-Thouless type behavior. Your TC will get shifted up by an amount that's, you know, only logarithmically small in the interplane couplings. Now, this is better for an antiferromagnet. You can imagine having antiferromagnets where the interplane coupling is frustrated. So here's a picture. This actually turns out to be a picture of what undoped lanthanum cuprate looks like, where you have an antiferromagnet in one plane. The antiferromagnet in the next plane has its sites above the plaquette centers of the plane below, so that the coupling of the Néel order in neighboring planes is 0. And So they're decoupled from each other. That's why one's able to see such good 2D antiferromagnetism over a broad range of temperature above the Néel temperature in lanthanum cuprate. You know, since Shivaji's here and he likes order by disorder, indeed, there are higher order couplings that are always generated. For instance, couplings of this form, but those are going to be small in proportion to the square of the ratio of the interplane to the in-plane coupling. Okay, so, and this is not only why you see 2D antiferromagnetism in lanthanum cuprate, but you actually also see rather long-range antiferromagnetic stripe order, which is totally uncorrelated in the third direction. Okay. Okay, that's what I said. Okay, so let me. Okay, so what does this have to do with the PDW? Well, if the PDW follows the structural motifs of this particular material, what we expect is that the pair density wave will have its ordering vector along the x-axis in one plane, along the y-axis in the next plane. So think of this as being an antiferromagnet, and you can immediately see that the interplane coupling is frustrated. The lowest order Josephson coupling between pair density waves is 0. And so that's our explanation for how you can see this 2D superconductivity without triggering 3D superconductivity. Now I'm going to come to Duncan's question. So here I looked in one special cuprate which shows this layer decoupling, which is a spectacular but rather special set of phenomena. Most cuprates don't exhibit layer decoupling. Do we think that they nonetheless have a pair density wave? So there's a way to look for that. We know that we can see these charge density waves orders, which I'm going to call a 2Q peak for the reasons we discussed. That's what, it's the charge density wave. But if I were to attribute it to being a signature of pair density wave, then it would be the 2Q peak that comes from the square of the pair density wave order parameter. But if I then can arrange for systems where I expect to have both pair density wave and uniform superconductivity, I should also see a 1Q peak. And this should occur, for instance, in vortex cores where the uniform superconductivity is suppressed and where pair density wave occurs. Okay. So I just remind you of this. There's the 2Q peak. Here's the 1Q peak. And here is the attempt to see a 1Q peak in LBCO in a range of magnetic fields to tune the relative strength of the pair density wave and uniform superconductivity. Here you see, as the magnetic field is turned up, the charge density wave strength at 2Q, in this case here around 0.68, turns up. And as you see, there's absolutely nothing at 1Q. So this proves that there isn't pair density wave here. Well, proves, I would like to make sure that we can see it where we want to see it. So I'm now pressed on time, but let me now return to this material. Let's look both just below here where we think we have pair density wave and as close as we can get down to here where maybe we have both pair density wave and uniform superconductivity, and see if we can find a 1Q peak. And this is done with resonant X-ray scattering, resonant elastic X-ray scattering on two particular cuprates in this family. And now, okay, so here's the actual data. I did want to show you this. Here's the 1Q peak, which is the 2Q peak, which is a very, very strong charge density wave peak, which you can just barely see in the raw data. So this is different temperatures. This is above the charge density wave ordering temperature. This is below the charge density wave ordering temperature. And this is at the lowest temperature that they can reach. This is a very strong peak, which you can barely see in this. Here's where the 1Q peak is. This is the signal that I'm going to claim victory on. Okay, so let me blow up this region. What you can see is the scattering strength at this wave vector is temperature independent as I lower it from 60 Kelvin to 43 Kelvin, and then there's excess scattering when I go down to lower temperature. It's well known that this is a feature of resonant X-ray scattering. You have a big fluorescence background, which is Q dependent, but temperature independent. So the way people always interpret this data is to subtract a high temperature signal, which one assumes to be the background, from the low temperature signal. And so that's what I'm doing here. So this is the difference between 43 Kelvin, just below the PDW ordering temperature, but far from uniform superconductivity, where you see a very strong 2Q peak, but nothing at 1Q. And then this is going to the lower temperature, where this 1Q peak appears very clearly in the difference spectrum. Okay, I'm out of time. So there are lots of checks of this. This is a different material, same sort of analysis. If you ask me questions, I can tell you some of these things. Okay, this is, I'm copying Mike. He went through the technical stuff at the end quickly also. And now let me conclude. So I wanted you to be aware of the background subtraction. It is standard, but it's a big background subtraction. Modulo that worry, this is as close as one can find to a smoking gun of this pair density wave. And conversely, having seen this 1Q peak in the material where layer decoupling made us think there should be pair density wave, the absence of this 1Q peak in YBCO should be taken as serious negative evidence. So this falsifies the mother of all states proposition. Okay, so I'll stop.
What is the dependence of this 1Q peak on a C-axis momentum?
Yeah, so that's interesting. So that was one of the things I flashed by, and since I can't get this to work, if you look at L equals a half, you see it. And if you look at L equals 1, you don't. Okay, that's the only two data points we have, but that's very important. So the charge density wave peak is known to be peaked at a half. If the charge density wave were a PDW harmonic, it would have to be peaked at 1. This 1Q peak is peaked at the same value of L as the PDW state, which is, again, for this, consistent with it being a harmonic.
So far, I assume there's no phase information in this. So it's not a phase-sensitive experiment. But have they tried changing polarization or something? Because I know the background can be subtracted if you hear that Is it change polarization of the incoming X-ray? What happens to this 1Q peak? Is there any predictions on that?
I mean, so here the 1Q peak is a charge density wave. So its phase is a center of mass motion. And no, I mean, there's no information on that. That still wouldn't tell us much about pair density wave. Now, Dale has some data that, you know, he refuses to publish, which is close to being a phase sensitive measurement of this, and it's certainly very encouraging. Phase sensitive in the superconducting sense.
Understood, Lord, correctly.
Yeah.
Regarding the CX study.
Yeah.
There's a wide temperature regime in which some of these cuprates show essentially vanishing resistance that they're not.
No, yes, exactly. Yeah. So indeed. So let me go back and show the data on that. I didn't skip it. There it is. Okay, so here you can see things on a logarithmic scale. So you can see, so first place, this is zero field cooled. This is field cooled. This is for the magnetic field in the C direction. This is for the magnetic field in the AB plane. The scales are the same here, but this is logarithmic. So what you can see is that you do start seeing some diamagnetism here, right? You don't get full Meissner screening until you go below 4 Kelvin. So what's going on here? Well, so certainly this isn't a superconducting state. If it were a superconducting state, at least for the field perpendicular to the planes, it should exhibit a Meissner effect. So this is where I disagreed with Eduardo here. What I believe is going on here is that we have pair density wave with long correlation lengths in the plane. That's not as crazy as it sounds. With a superconductor, once the correlation length gets long, you just lower the temperature a little and it's going to be infinity. But the pair density wave, because it has a charge density wave component, couples to disorder. And so if I imagine that the pair density wave correlation length is roughly the same as the measured charge density wave correlation length, which is something like 400 angstroms, okay, I've got really significantly large patches of superconductivity, but they're still not true superconducting long-range order. And they're more or less uncorrelated from plane to plane. So it's only at lower temperatures where I start getting some uniform superconducting component that I get into a true Meissner state. I think this also explains, I mean, you know, there should be higher order Josephson couplings. So if we had true long-range PDW order in a plane, then even though I've frustrated the leading order Josephson coupling, it should still order. So this is a piece of the story I didn't want to get into, but it is a feature of pair density wave that it is sensitive to disorder in the way that uniform superconductivity is not.
So you didn't mention
So I didn't mention what?
They say evidence for 1Q.
So indeed, so so there's one other material where there is direct evidence for this 1Q peak, which is in bilayer BISCO. In STM studies, they've seen a 1Q peak in vortex cores. The reason I didn't mention it is the same thing has not been seen in bulk measurements on the same material. So I mean, I like that data, as you know, I think it probably is seeing pair density wave, but I wanted, since I wasn't talking to a group of experts, I wanted to tell you things that I was certain were right. And there is this puzzling feature that in a magnetic field for the same material in the same range of magnetic fields, this 1Q peak simply doesn't show up in bulk measurements. Yeah.
With, say, nearest neighbor, next nearest neighbor. What's the evidence?
So, do you have a few days? So, there are various approximate solutions of the TJ and Hubbard models that give pair density wave. Maybe the best are, there are IPEPS calculations which show the pair density wave ground state. And they show actually that the pair density wave and the uniform state are very close in energy. Unfortunately, results that I understand how to think about because they converge to the right answer, namely DMRG calculations, have really refused to give us a pair density wave. And, you know, motivated by the fact that the IPEP said that the pair density wave must be almost degenerate, I figured I didn't have to be smart, I just have to be energetic. So we tried the TJ model with different values of first and second neighbor hoppings, with different values of nearest neighbor and next nearest neighbor J's. We found slews of states. As you change these things, the nature of the ground state changes. It's really, this intertwined orders is a real fact. There's lots and lots of states that are really close, different period charge density waves, insulating, conducting, but we never found a pair density wave. There are models that you can construct that have pair density waves, but they're very far from being natural models for the cuprates. So that, okay, there seems to be some new data coming out of DMRG studies on the Emery model, the 3-band model, that look more promising for pair density wave. But
These 1-band models, they don't have basically the wave function that's trivial, right? The tight binding models, and the 3-band models that wave functions are not trivially projected to the 1-band. Is that what
I don't think so. Okay, but yeah, for most properties that the 1 and 3-band models seem to give, you know, there's some complicated dictionary about how you relate them, but I think there's no obvious fundamental difference between them.
But wouldn't you, if you think that this is not a ubiquitous space,
Yeah.
and it happens to be particular to this region of space,
Yeah.
then you don't need to get it from the Hubbard model. Might be a peculiarity of this little region of, in fact, isn't that consistent with what you're saying?
It is. So that's you're an optimist. You're putting a good spin on it. You know, that not only have I had a hard time finding the pair density waves, but God has also had a hard time finding it.
It depends on you. Okay,
It's a big industry fire, where somebody here was also talking a bit about forming pairs of people.
Yes. Yeah.
Argument that pair density waves was the key thing.
Yeah. So that's right. So if you have a pair density wave and you melt it in various different ways, one of the things you can end up with is a charge 4e superconductor. And that, you know, so, you know, given a pair density wave, it's dead easy to construct a charge 4e superconductor.
There are some details.
Yeah.